The thing that has affected both you and myself most profoundly is the existence of something called spinors at the core of our understanding of matter. Do you want to say a little bit about what that is, why you think it's affected you and me as well, and why perhaps it hasn't had the same emotional or intellectual impact on the community?
Right. I mean, when physicists more or less completed what's called the standard model of particle physics, right? You have the known forces in physics, like the electromagnetic force, the weak force, and the strong force, as well as the force of gravity. And then you have the matter particles, which are electrons and quarks and neutrinos and other generations of these that form what are called the fermions. Okay, and these are called the matter particles. And they have mass because of the interaction with the Higgs boson, right? Which is sort of in between.
It's not going to make sense to people.
It's not. All right. But anyway, the force particles behave differently as elementary particles under rotations than the matter particles. All right. So these matter particles, you have to basically rotate them 720 degrees to return them to their original state. All right. Whereas most objects, you rotate it 360 degrees and you get back to where you started. All right. But spinors are different. Right. And they behave in a very specific way. And there's a very specific way of describing them mathematically. But it's described in an unusual way. It's described as a column of complex numbers or a column matrix, if you like, that's acted on by a rotation matrix that tells you specifically how these particles transform under rotation.
Honestly, that wouldn't make any sense to me. And I don't think I can help all of my audience to get it.
This is the thing. So this is the way physicists are introduced to a description of electrons.
Well, look, can I just try to play with something while we're talking about this in this way?
Well, you can. Can I hand it off to you in about 10 seconds?
No, you finish it out.
All right. So I found this description to be incredibly unsatisfying. All right. Because the rest of physics is not described this way, right? You don't introduce a fundamental field that transforms a certain way under rotations. That's not how, why would the universe do that? It's not elegant. It's not geometric, right? It seems sort of arbitrary. Why would the universe have spinors in it? Well, it turns out that because if you describe general relativity as curving four-dimensional space-time, describe gravity, and you describe forces as gauge fields, right? Both of those are very geometric descriptions. They're very elegant mathematically. And then you describe the fermions as spinors. It looks like a kludge. It doesn't fit with the other theories. But that's why I left physics to solve this problem. I wanted to know why spinors geometrically. And no one else was interested in the problem. No one else thought it was a problem. They're like, yeah, they transform this way, and maybe it comes from strings, and that's all you get. And it's like, no, that's totally unsatisfying. If gravity is described geometrically and all our other forces are described geometrically, the universe is just one thing. It's right there in the name. I mean, una is one, verse is turning. We have this one turning thing we call the universe, and it's just one mathematical object. And if we have different particles, they have to be aspects of this one mathematical object. Why would this mathematical object have spinors as an aspect of them? It was a huge mystery to me. I wanted to go solve it. No one else even acknowledged it was a problem. And you also tackled this. This also bothered you.
Well, so this is the very difficult part of what the portal is supposed to be. And I have the feeling that we've probably left a lot of our listeners behind, but I've said that we're going to have to take some risks, and this is going to be one of them. So the way I see it, some of our listeners are also viewers, right? And we have in studio these beautiful Klein bottles from Acme Klein Bottle and Cliff Stoll out of Oakland, I guess. These objects that I'm holding up, or you can look up Klein bottles on the web, have this very odd property that they are covered, if you will, by the surface of a donut if the surface of the donut wraps around this object twice. And we call this a double cover. Now, the idea that you have some very strange object with no inside and outside, called a Klein bottle, but that it's wrapped twice by some object which has different properties, namely the surface of a donut called a torus. The rotations of our three-dimensional space bizarrely have some object that covers them twice, just as a donut covers a Klein bottle twice. So when we talk this crazy language about you have to rotate an object more than 360 degrees for it to come back to itself, this is somewhat of garbage language that we've taught people to understand, where we're not really showing them what's behind the curtain. We're not showing them that there are the rotations of a rigid three-dimensional space, and then there's this thing that covers those rotations twice called the spin group. And that spin group is the thing that has the property that it acts on these things called spinors. Right. So this is a hidden level of structure that you would not know was there just from three-dimensional space. There's some secret trapped in three-dimensional space that is very well hidden. And if we weren't at a very high level of mathematics or physics, you would never know that spinors even exist to play with.
Right. I mean, it comes out of representation theory, but that, once again, that's a fairly high level of mathematics you have to get to even see that these things exist.
And for all of the other basic kinds of symmetries, we don't have these hidden representations. We don't have these hidden spaces that have these bizarre properties. It's only for these things called orthogonal groups. So it's a very special property of real Euclidean rigid space that spinors are there to be found. And not only does nature find them, she bases all of matter around the hidden object that can't easily be seen or deduced, which is a total mind job.
Right.
And the math community has, in fact, sort of split between people who think, hey, we can describe these things mathematically, so our work is done, versus other people who believe there's something about spinors that just, it continues to surprise us. We don't understand where they came from. They're a hidden feature of the universe, and they keep giving in this very mysterious fashion.
Yeah. And the most of the general relativists who came at this problem just would not want to touch it because it's too foreign to them. And the people who came into it from the particle physics side thought it wasn't a problem. It's this field transforms a certain way. It seems perfectly well described to me.
This doesn't make sense to me at all. So
it didn't make sense to me either, Eric. That's why
let me give you an argument as to why this is a really serious problem. Huh. If I take two kinds of thing that one might hope to find in the universe, an electron and a photon, okay? So the idea is that I've got stuff that orbits around atomic nuclei, and I've got light and its relatives that carry the electromagnetic force in the photon. If I don't know how to measure length and angle, I can still talk about the objects that are photons. We call them spin one particles. But if I don't have length and angle, I don't have any way of talking about spinors. Right. In other words, if there isn't a ruler and a protractor, which is effectively what Einstein used to define space-time, I don't have an ability to talk about spinors. And that's a big problem, because if you're going to... It's
not just a problem, it's a huge clue. It says that spinors have to be intimately related to gravity and general relativity.
And gravity. So spinors are over on the quantum side of the equation. Right? In the children of Bohr, it's really more their object than the children of Einstein's. The children of Bohr claim we have to quantize gravity and make everything quantum. So it's sort of an imperial belief that the people who study the Standard Model should extend their techniques to cover gravity so that all can be one. Yet, if it turns out that we don't know how to measure length and angle between measurements, because in quantum theory you get something very different when a field is propagating versus when it's measured. All of the probabilistic stuff we talk about is happening when there's a quantum measurement. Mm-hmm. If you don't know where length and angle are while something is propagating, then you don't even know where the electrons can be a disturbance. If electrons are waves, they have to be waves in some kind of a sea. You know, with photons, that you can't tell exactly where the wave is, but you know where the c is. In the case of electrons, if you don't know where the metric is, you can't even say where the c is that the electron would be a wave in.
That's right.
And it's a very convoluted thing, but it's a big difference.
Yeah, and I can almost describe it in extremely simple terms, which is most physicists who think about it, think of gravitational charge as being mass. But gravitational charge is really spin.
Well, we're getting pretty we're getting pretty far afield.
All right. So to speak.
So to speak. So let's imagine that maybe our listeners haven't understood exactly what we're saying, but that there is some special problem about spinors and how they're tied to the structure of space-time that is different, where you can describe things like photons in some sense without knowing how length and angle are measured, whereas length and angle are essential if you're ever going to talk about spinors.